let us see how far we go. Okay. So, one of the most okay, lookup tables, right. I tell you that lookup table is a linear function approximator. Do you agree with me or not? Right? How, what will be my phi? Huh? Phi would be an indicator function, right. So, phi I of S will be 1 if S equal to Si, right. So, that essentially becomes a linear function approximator, right. So, well, you do not want to use that, is a useless function approximator, but just useful to think about it that way. Now, I can define another form of indicator function approximator, right, known as state aggregation. So, what is state aggregation? Let us say that I have a very large state space, right, very large state space. I can typically assume that states that are close by will have the same value, right. Suppose I have a million by million grid world, right. If I assume that states that are say within 10 of each other, right, like a 10 by 10 grid, I can take any 10 by 10 grid and the states will have the same value within the 10 by 10 grid, right.
Having a state value same is not right.
Why?
You can have like an average of the ones around you makes more sense.
No, that is you are moving into nearest neighbor kind of a setup. We are not talking about that. I am just saying that given that I have to reduce this, right, I have a million by million, right. So, how much is my value function going to change if I move 10 states in one direction? I have like another 999,990 states there to go.
So, we are trying to reduce the dimensionality.
I am trying to reduce the dimensionality, I am trying to reduce k, right. So, if I had done a lookup table, right, my k will be a million squared, right. I am trying to reduce the dimensionality of that, right. I am going to say that is another kind of an indicator function. Instead of saying that it is exactly this state, I am going to say it is one of these 100 states.
How is it on policy then? You are in one state, you are
It is still on policy. The samples are still on policy, right. The sample generation is still on policy.
sampling from around that state.
No. I am just sampling a trajectory, right, following pi. It is not like I am jumping around and sampling things. There is some amount of reduction of information here, right, but still the sampling is still done on policy, right. So, I can use this indicator function which says that I am in this big grid, right. So, I can take this large, okay, I will take this large grid world, right. It has to have an odd number of columns. Now, I break it up into, instead of having 30 indicator functions, I am going to have only 9 indicator functions. Instead of having 30 indicator functions, I will have 9 indicator functions, right. So, this kind of an approximation is called state aggregation. This kind of approximation is called state aggregation. Because we are talking about grid worlds, I am drawing squares, right. If I am talking about say a continuous world, right. So, for example, talking about like a robot navigation problem or an arm manipulator, things like that, where my states is given by joint angles or something like that, and I am going to have a continuous state space, right. So, I can talk about any kind of compact state, right, in that state space, and I can talk about memberships of that. Right. So, for example, I can take this, it is a continuous state space, right. I can start talking about right. I am going to put this kind of circles on the on the state space, right. So all states here, this is an indicator function basically. For all the states here, this will be 1. For all the states here, this will be 1. For all the states here, this will be 1. So what is the problem with this? It is not covering the whole space, right. So typically what happens is you end up actually covering the whole space. Okay. Now what is the problem with that? Overlaps. So what is the big deal with overlaps? 2 indicator functions are going to come on instead of 1. Better, huh? Why? The generalization would be better. See, earlier I was telling you when we did the grids, right, when we did the state aggregation, I was telling you that any block of 10 states I will take, it will have the same value, okay. But that is not true in the representation I am using here, because there is going to be a discontinuity here, right. These 4 states will get one value because the average of these 4, that is essentially what will happen, right. It will learn to be the average value. If you look at how the update happens, right. So every time I come, I will update the same value, right. So it will learn to be the average of these 4, and this will learn to be the average of this 4, but these 2 which are actually right next to each other will have a drastically different value, right. When I start doing this overlap, so what will happen is, well, these will get updates together, likewise these will get updated together, but the states here will actually get updated for both. Essentially it will convert to the average of both, right. So it will not be a abrupt shift from one to the other, it will be more like a, well, step, okay. It will not be a graded shift, it will be based like this, there will be one intermediate value which is the average of both, and then another one. So it will not be a complete jump, it will be a gradual jump, right. So it is okay to have this kind of overlaps. In fact, you could argue that it is desirable to have these kinds of overlaps, right. And this way of, and again we did nothing here, nothing fancy here, all of these are indicator functions still, except that depending on the degree of overlap, that many indicator functions will come on for a state, right. It could be 1, it could be 2, it could be 3, it could be more, right. Why? Compute the what? Domain knowledge, intuition, tarot cards, I mean this is why deep learning is becoming popular nowadays, because you can use deep learning instead of the tarot cards, right. So you have to use some kind of, in this case I am assuming all of these are geometric problems, right. So I am assuming nearness in the particular metric space I am looking at indicates nearness in the value function. It will not always be the case, right. So there are people who actually look at, so the way to address this is to take the state space that you have, embed it in some manifold where the nearness in the distance actually means that you are near in value function as well, right. So there are many methods which people have used it, they try to come up with different kinds of basis functions which have that kind of, so the basis function would be what are my basis functions here, in this particular case whatever we are talking about, what are my basis functions? Yeah, the phi1, phi2, phi k. So I am using some k basis functions here. So people have come up with different ways of transforming these bases, so that nearness in that transformed space, right, indicates nearness in the value function as well, right. So this is an example that I was giving yesterday. Right. So take a grid world or take some space like this, right. Let us say I have some goal there, right, and say my parameterization consists of the x and the y, and for every time step I have not reached the goal I get a reward of -1, right. So how will my value function look like? Well, in the negative direction, assuming the negative direction comes out of the board, right. So it is going to look like this, right. So it is going to slide all the way in. So the peak will be somewhere here, right, and then from here there will be a gradual decrease all the way to this point, correct. So that is a nice smooth value function, right. In fact I can think of, depending on my dynamics and stuff like that, that could even be linear, right. So it could be just a plane tipping, so it could be a plane that is tipped over like this, right, that should be fine, right. So I can take a sheet which like this, and then I can probably represent using a linear parameterization. Great. Now what I am going to do is, I am going to put a wall. Now what is going to happen to this? There will be some kind of a discontinuity. So where will the discontinuity be? So here it will be nice and small thing, here it will be a much larger value, right. So one way to fix this is to think of some kind of an embedding where I essentially split the room open like that, right. So I essentially think of in reality that is what it is, right. If you think about it, I have now, in fact I made it into some kind of a quasi corridor by drawing the line there, right. So I can think of transforming a space into something like this. Now if I look at the xy coordinates here, right, it might be a good enough approximation for the value function, right. So it could be a good enough nearness estimate. I mean, obviously this is not what you have to do, you have to look at a more complex embedding. I am just trying to give you some intuition as to what you try to do when you find those embeddings, okay. You try to get a transformed space, so that in fact if you think about it, so my y coordinate runs like that, okay, here. So it is not a proper linear thing, so this will be my y coordinate, right. So something like this will, I will have to think about, right. So it is a complex thing. So but people do work on stuff like this, right? They look at all kinds of different bases, so that you can do this kind of generalization at the end of the day. So we will not worry about that, let us stay in the a more innocent world for the time being, where we assume that this kind of a generalization is fine without having to worry about any other basis transformations, okay. So this is called coarse coding. So I am doing some very coarse representation of the state, right. So it is sometimes called coarse coding. So the problem with coarse coding is that there is no uniformity in the number of bits that I am using for, I mean number of on bits, right, I am using for representing a state. So some states could have only one bit, some state could have multiple bits, and so on and so forth. And so you could, people came up with a more systematic way of doing this coarse coding, okay. And as with many of the things as described in the book, this is not the way they came up with whatever I am going to talk about, right. So they do something called tile coding, right. So I am just going to use this space because it is the last thing I am going to do today, so I will stop with this. Right. So let us consider some input space, right. So tile coding does the following, right. And it splits it up into this kind of regular tiles, okay. But this is not giving you that nice overlap features that the coarse coding had. It is just almost like state aggregation. So what tile coding additionally does is that it does not do one such grid, it does multiple such grids. Okay, that's got really confusing, but it's very simple. If you think about any state, any point in the state space, it will always light up two of the indicator functions, one from the green grid, one from the yellow grid, right, and it gives you this overlap that you wanted, right. So all the states in this yellow grid will get updates from this place, and all the states in this green grid will get this update from this state. So in some sense you get the overlap, right. So there is some set of states here which contribute to this, which do not contribute under the green grid. So there is some amount of overlap that happens from one cell to the other, from the green to the yellow and vice versa, right. So it gives you the advantage of coarse coding. It's a form of coarse coding, but it's more systematic because every state will have two indicator functions lighting up, right. So each one of these is called a tiling, right. So that's a tiling and that's a tiling, and each one of this is any guesses? So each one of those is a tile, and the whole grid that we talked about is called a tiling. So in this example I use 2 tilings. People typically use like anywhere between 4 to 7 tilings to get good performance, right. And so how many indicator functions light up for a given input state? Number of tilings, right. So as many tilings as there are. So if I have 7 tilings, there will be 7 things that light up, right. So it turns out to be a very good function approximator for many RL tasks that people were looking at about 2-3 years ago, till about 2-3 years ago. So this turned out to be a really good. So obviously you can't play Go or backgammon using tile coding, right. You need something more cleverer than that, right. It turns out that you need something more. So that's the biggest advantage of all these deep learning methods is that you do not have to define the phi, okay. They find the phi from the data. That is the biggest advantage of many of these tile coding methods. They just find out what are the appropriate phi from the data itself, and then uses that phi to define a value function, and then learns those value function. Everything is done in one shot. It is not like I first learn the phi and then learn the value function or anything. It is a single network. As I keep training it, it learns the phi and the value function also. This is amazing thing, right. Looks like you are getting a lot of advantages for free. What is the downside?
Lots of data.
You need significantly powerful computing equipment first, otherwise it is not going to run anytime soon, and you need a lot of data, right. So that's some of the biggest challenges. So tile coding, one popular instance of tile coding was a specific thing called CMAC. So CMAC stands for, you should tell me now, cerebellar model actuation controller, right. So essentially it was originally proposed as a model of the cerebellum, the human cerebellum, right. And so from there cerebellum, and then from there I mean, of course it's, I do not know if people still consider it as a serious model of the cerebellum, but this comes from way before, like in the 60s or 50s and 60s, okay. There is a guy called Albus who proposed the CMACs, and it turns out that CMACs do some kind of tile coding, and then they do a whole bunch of tricks to compress the tilings, right. So nowadays with a lot of memory at disposal, you wouldn't want to compress the tilings, but the classical CMAC implementation uses a lot of hashing based tricks to compress the tiling representation, so that you do not have to store the entire vector theta, right. If you think about it, suppose each tiling is 10 by 10, right. So, I have number of tilings into 100 thetas, right, and if my tilings become more and more finer, right, and the state space is very large and I want to keep smaller tiles, right, then the number of thetas that I need to store becomes larger and larger. Right. I do not actually have to store the tiles themselves because they are so regular. I can have some kind of a function, right, that computes the tile memberships. I can have a functional form that will tell me which tiles come on, right, but I have to store the thetas. Right. At the end of the day, this is also a lookup table, right, except that I determine the membership, which entry I look up in the table in a very complex, systematic but complex way, right, instead of just looking at the index. Right. So, people use hashing, you know how you can use hashing to compress tables. So, just like that they used hashing to compress the entries in this, and so it has advantages and disadvantages. In fact, it gives you unintended generalization, right, because two different tiles could be hashed to the same weight, right. So, one tile from here, right, one tile from here, another tile from here could hash to the same weight. That gives you some kind of destructive generalization, right. But then there are some conditions under which you can show that this is not too bad and so on and so forth. But I personally do not like hashing, but we have found out that in some cases on very large state spaces, having hashing actually helps you to learn faster, which we really have not managed to explain why that is the case though. Okay. So, I will stop here then. So, we will talk about eligibility traces and control and other things in the next class.